Welcome to everybody. Thanks for joining. We're really excited to have Hirofumi here today. In addition to a whole bunch of different parts of ASR and speech translation, he's also been working on simultaneous translation, which will be the subject today. And I'm really grateful as well because I've started using ESPnet. So just in general, it's awesome to connect a little bit more and get a chance to actually chat. Yeah, if something comes up that you want like urgently answered so that you understand the rest of the talk, please free to raise your hand, or maybe better, put a question in the chat and we'll try to pause and answer it before we go on. But for the most part, we'll collect questions on Dory and hopefully have a nice discussion at the end. So yeah, with that, I'm turning it over to Hirofumi. You can start, and yeah.
Okay. So hello everyone. I'm Hirofumi Inaguma, last year PhD student at Kyoto University, Japan. Advised Professor Tatsuya Kawahara. And first of all, I'd like to thank all the organizers for inviting me this talk. And my research background is speech, and I'm very glad to share my recent works with people in the NLP community today. So let's get started. Okay. So this is today's agenda, and I have two main research topics today. The first topic is streaming end-to-end speech translation, speech recognition, based on monotonic chunkwise attention called MoCA model as a backbone. And I will show you how to reduce latency with alignment information. And the question is, where is a good place to apply alignment information in the encoder-decoder architecture? And also, I will show you how hybrid ASR-free alignment information, which is extracted from CTC model. And next topic is non-autoregressive end-to-end speech translation towards fast and accurate decoding. This is based on conditional masked language model, which was recently proposed in the text-based machine translation community. And I will show you how to estimate target lengths from speech directly. Okay, so let's start from streaming ASR. So firstly, let me describe the background of hybrid system. Hybrid ASR system is a traditional approach in ASR, and this is still dominant approach in production systems in the industry. And the hybrid system decomposed conditional probability of target transcription given input speech based on Bayes rule, and then the probability is decomposed to acoustic model and language model. During inference, the best word sequence can be estimated, but this word sequence is decomposed into pronunciation with pronunciation dictionary and further decomposed to HMM state, which was estimated from GMM from scratch. Hybrid system is very good at recognizing rare words and suitable for low resource scenario. And it is very easy to update every single module, but it requires expertise knowledge. So recently, end-to-end ASR systems have been investigated. End-to-end system try to learn direct mapping function from input speech to target transcription to maximize the probability of transcription given input speech. This end-to-end structure is very good, very suitable for quick model development, and it is also scalable to large amount of training data. But end-to-end speech recognition is not good at recognizing real word, and also when updates when we want to update the model, we need to update the entire model. And the end-to-end model can be categorized into two directions, time synchronous model and the label synchronous model. Time synchronous models include CTC, RN transducer, and recurrent neural aligner, and where the input sequence lengths and the target sequence lengths are the same. In contrast, label synchronous model can generate variable length of output sequence, which includes attention-based RN encoder decoder and transformer. Okay, so streaming SR is one of the most important applications for speech recognition. The task is to transcribe speech before a speaker finalizes their turn. And there are a lot of expected applications, including live captioning, dialogue system, and simultaneous machine translation. Currently, RN transducer is dominant in the industry for streaming usage. This is because RN transducer is stable for streaming inference thanks to frame-wise prediction. But RNT is memory consuming during training, so we need to reduce the mini batch size. In other words, it is RN transducer requires distributed training and efficient implementation and small vocabulary size. Moreover, during inference, since such space is relatively large, so the inference speed is very slow, although it can be optimized with C++ and so on. So however, in the academia, it is not so easy to build good RN transducer. So I'd like to focus on label synchronous streaming SR in this work. And the label synchronous model is very suitable for smaller memory consumption and fast inference. But there are two main challenges in label synchronous streaming models. The first one is we need to modify the decoding scheme because the naive implementation of sequence-to-sequence models require the whole encoder outputs to generate the first token. Moreover, sequence-to-sequence model suffers from poor performance for recognizing long-form speech because of exposure bias problem. This is which is not occurred in frame synchronous models such as CTC and RN transducer. Okay, so to make encoder decoder models streamable, there are a lot of streaming attention-based encoder decoder models, and the attention-based streaming models can be categorized into two main directions. The first category is the model which learns when to segment audio on the encoder side, which include triggered attention, adaptive computation steps, continuous integrated amplifier, and the neural transducer. In contrast, monotonic chunk-wide attention, MoCA learns when to segment audio on the decoder side by considering the context information. So in this study, I will focus on MoCA because MoCA is a simple framework and achieved a good result on a lot of benchmark datasets. And also, training is very efficient, and more importantly, during inference, the decoding complexity becomes linear. So I will first introduce MoCA framework. MoCA behaves differently between test and training time. At test time, MoCA, So MoCA introduced two kinds of attention mechanism, hard monotic attention and chunk-wise attention. Hard monotic attention model whether to attend or not to at every single encoder output which is represented by black points in the figure. And chunkwise attention performs soft attention over a small window of size W from every single boundary detected by hard monotonic attention. However, this hard assignment is not differentiable. To this end, Mocha calculates expected alignments probability during training by marginalizing all possible passes using transcriptions. And the expected alignment can be calculated with bottom right equation. And this alpha can be implemented very efficiently in parallel with input indices J. Okay, so however, there are some trade-offs between latency and accuracy in streaming SR. And in streaming SR, future information that is look-ahead acoustic frames is very important to improve accuracy. As you can see from the figure, a large look-ahead acoustic frames leads to better word error rate, but it also leads to large algorithmic latency during inference. But this algorithmic latency can be controlled on demand. Moreover, there are some uncontrollable latency in the end-to-end streaming models, which is called delayed token generation problem. The figure shows the decision boundary predicted from Mocha, baseline Mocha model. And yellow dots represent the boundary location from Mocha. And you can see decision boundaries are delayed from the corresponding acoustic boundary. This is because the encoder is unidirectional, so future information is lacked. And also, the model is optimized with sequence level criterion, that is cross entropy. So the model can utilize as many future frames as possible to maximize the log likelihood during training. And this leads to increasing user perceived latency, which is not desirable in the real world applications. Similar behaviors have been investigated in CTC and RN transducer, but there were no previous works on attention-based encoder-decoder models. So the goal of this work is while keeping recognition accuracy at the same time. So I propose to leverage external frame level alignments extracted from hybrid system. So the question is where to apply alignment information to streaming encoder-decoder architecture. So I will propose 4 methods applicable both on encoder and decoder sides. I will first propose 2 methods applicable on the encoder side, and next propose additional 2 methods applicable on the decoder side. This is the overview of proposed method, and I'd like to start from the encoder side. The first proposed method is multitask learning with frame-wise cross-entropy objective. And I introduce additional objective function based on frame-wise cross-entropy objective, which can be calculated by using alignment information. The motivation to do this is we want to align encoder outputs to the true acoustic location. Inspired by the previous CTC work, I insert additional 2 linear bottleneck layers after the encoder layer. During inference, this frame level cross entropy layer will be discarded. The next proposed method is pre-training with frame-wise cross entropy objective. In the first stage, we train encoder with frame-wise cross entropy objective only. Then we will continue to train both encoder and decoder with the original cross entropy. And by doing this, we don't have to carefully tune the weight for frame-wise cross entropy during training. Okay, so next is a method applicable on the decoder side. The third method is delay constrained training, DeCoT. And here, I modified the alignment probabilities during marginalization. And I will remove alignment paths which surface uh, corresponding word alignment extracted from hybrid system. But the exact removal is too strong constraint. So I will introduce a controllable fixed acceptable latency delta. This is a buffer size. And once the alignment surpasses the predefined threshold, I will zero out such probabilities during marginalization. However, the summation of alpha will be much smaller than 1, so this is problematic for the optimization. To tackle this problem, I will introduce additional regularization term to keep the summation of alpha to be summed up to 1 during training, and I called this quantity regularization. And this quantity loss will be added to the original cross entropy. The last method is minimum latency training. And I will directly minimize the expected latency. And this expected latency can be calculated with time difference between reference boundary and expected boundary. Expected boundary can be calculated with the alignment probability. Unlike DeCoT, here we can reduce latency more flexibly because DeCoT assumes the fixed latency for every single token. Similar idea for differentiable latency loss has been investigated in simultaneous machine translation, but in speech recognition, there are a lot of silence frames, and non-silence frames are not distributed uniformly. So it is not so easy to directly apply the method in text-based model. This is an experimental condition, and I will use Microsoft Cortana voice assistant dataset, which consists of 3.4K hours data. And in order to convert word level alignment to subword level alignment, I divided time duration per word by the ratio of the character length of each subword. And to stabilize training, I performed warm start training where the DeCoT and MinLT were started from the baseline Mocha. And for the latency evaluation, I will introduce new evaluation metric, corpus level token emission latency. And the definition is the averaged time difference between a predicted boundary and the corresponding gold boundary. And I will report 15th and 19th percentile latency. And when calculating this latency, the teacher forcing was performed in order to match the sequence lengths between hypothesis and reference. This is a result when applying alignments on the encoder side. We see that multitask learning reduced latency in proportion to lambda CE, while degrading word error rate slightly. And pre-training also reduced latency, but it degraded word error rate too much. These findings contrastive to previous work based on CTC. This is probably because Mocha is a label synchronous model, so frame-wise cross entropy on the encoder side is not compatible with label-wise cross entropy on the decoder side. Next is the result when applying alignment information on the decoder side. We see that DeCoT can reduce word error rate by a large margin while reduce latency moderately, especially for the tail parts of the latency distributions. On the other hand, minimum latency training achieved small word error reduction and large latency reduction. In other words, minimum latency training can shift the entire latency distribution to the good direction. The combination of DeCoT and MinLT reduced latency further, but this is too strong constraint, so the word error rate was degraded too much. This is an alignment visualization sample from baseline Mocha and Mocha trained with DeCoT. And we see that the latency was indeed reduced. And in other words, this is very attractive for user perceived latency and user satisfaction. In summary, alignment information for Mocha is beneficial when applying it on the decoder side. But this is not purely end-to-end modeling because we need a hybrid ASR system to generate alignment information. So question is, can we remove the dependency to hybrid ASR system for alignment extraction? So to this end, I will investigate alignment extraction from CTC acoustic model. Before talking about CTC, let me explain the optimization problems in Mocha. Since Mocha doesn't perform global normalization over the 4 encoder outputs, the summation of alpha is not guaranteed to sum up to 1 during training, which means alpha is not a valid probability distribution. So this can enlarge the mismatch between training and test time. And also, the decoder is autoregressive and alpha is not a valid probability distribution. So we can't use backward algorithm unlike CTC and transducer. So this is very problematic for long and noisy speech utterances. In summary, the Mocha model needs to learn a proper scale of alpha and accurate decision boundaries at the same time. And this imposes significant burden on the decoder. So to improve the alignment quality, joint CTC attention framework has been investigated for the offline sequence-to-sequence model. And here, the auxiliary CTC loss was added to the original cross entropy to encourage the monotonicity between input speech and output text alignments. And both branch share the same encoder to enhance the alignment. So let's see what happens if we apply joint CTC attention to Mocha. This figure shows the boundaries from both Mocha and CTC. And the spike representation is corresponding to CTC posterior probabilities. And we see that decision boundaries from Mocha shift to the right side from the corresponding CTC spikes. But CTC spikes locates around the corresponding acoustic boundary. This is because CTC assumes conditional independence per frame, and also CTC can leverage backward algorithm as well. So in terms of alignment quality, CTC is more accurate than Mocha. To this end, I propose a novel framework called CTC synchronous training, where CTC's posterior spikes are leveraged as reference boundaries for MoCA. In other words, MoCA is trained to mimic the CTC acoustic model to generate the similar decision boundaries. Then I introduce additional loss function to minimize the gap between CTC boundary location and expected MoCA boundary location. And to obtain the good performance for the baseline system, I also I further introduce quantity loss. But as shown in the later experiments, when using CTC synchronous training, we didn't use quantity loss. Okay, so next is the extraction of CTC alignments. Both branches share the same speech encoder, and we performed a force alignment with forward-backward algorithm over the reference transcriptions. And these alignments can be calculated with current model parameters. And then we extract the most probable CTC pass pi bar, and then however, there are several repeated tokens. So we will use the leftmost index for this purpose, for boundary purpose, and we will use the last time index for the end of sentence mark. Although CTC synchronous training is effective, applying it from scratch is not so efficient because the summation of alpha in the early training stage is much smaller than 1. So it is difficult to accurately estimate the expected boundary location. So we propose a simple but effective curriculum learning strategy composed of 2 stages. In the first stage, I will train BLSTM encoder plus MoCA with quantity regularization until convergence. Here, I expect the model to learn a proper scale of alpha. In the next stage, I will continue to train the latency control BLSM plus MoCA with CTC synchronous training. Here, I expect the model to learn accurate boundary location. When we want to use unidirectional LSM encoder, the same encoder is used in both stages. And next, I'd like to explain the relationships between spec augment and MoCA. Spec augment is one of the most successful data augmentation methods in speech recognition. And the spec augment introduced time and frequency masks and to improve the representation both in the decoder and encoder. However, if we apply spec augment to MoCA, the recurrency of alpha can be easily collapsed after the masked region, as you can see from the equation. So in my preliminary experiments, naive MoCA model didn't obtain any gains with spec augment. In contrast, CTC can estimate boundaries more accurately, even right after the masked region, thanks to the conditional independence assumption per frame. So in other words, CTC synchronous training is expected to improve the effectiveness of spec augment, especially for MoCA. Here is the experimental condition, and I will use TEDRIM2 and Lively Speech, both English corpora. And I will investigate both unidirectional and latency control LSTM encoder. During inference, I used shallow fusion with external 4 layers of LSTM language model. This is the result on TEDRIM2, and for the offline system, we see that quantity regularization was more effective than CTC synchronous training when applying it from scratch. However, in the streaming scenario, we saw significant improvements regardless of the type of encoder, and the relative gains are larger than 12%. However, the combination of the combination of CTC synchronous training and quantity regularization was not so effective. This is probably because CTC synchronous training has an overlapped effect to improve the scale of alpha. This is a result of curriculum learning, and we see that by seeding the model with BLS and Mocha, large improvements can be obtained. This is a result with spec augment, and consistent with previous work, we obtained a large improvement with spec augment for offline system. However, when applying spec augment to Mocha in the streaming scenario, we didn't see any gains. In contrast, when we apply CTC synchronous training jointly with spec augment, we obtained further 30.1 relative improvements. And this result, this best number is very close to the best offline system. And also CTC synchronous training was robust to the input mask size. This is a plot of word error rate bucketed by input sequence length. And we see that CTC synchronous training for very effective for recognizing long form speech as I expected. Next is a result on libre speech, and this should be the large scale experiment. And we saw the similar trend as TEDRIM 2. However, the relative gains were smaller than those on TEDRIM 2. However, when we use a unidirectional encoder, which is like a more bad baseline system, and we obtained very good improvements, more than 10%, and further improvements can be obtained with spec augment. This is a comparison with previous work based on RNN-based sequence model on libre speech, and our best model much better than previous works. Okay, so then the question is, which is better, hybrid SRR alignment or CTC alignment? And I did it on TEDRIM 2. And as you can see from the table, CTC synchronous training not only improves word error rate, but also reduces token emission latency at the same time. And also CTC synchronous training is as good as DeCoT and MinLT for latency reduction without relying on external alignment. Next is a result on libre speech, and when training data is large, CTC alignment becomes very accurate and reliable. So we achieved better word error rate and better latency simultaneously. Okay, so next topic is non-autoregressive end-to-end speech translation. Recently, end-to-end speech translation in which the model directly translates source speech to target text is an active research area. And the process of end-to-end approach is simplified architecture the avoidance error propagation from SR module and the low latency inference, and also endangered language documentation. However, end-to-end approaches generally suffer from data sparseness because of the lack of supervised training data compared to SR and MT data. So most previous works focused on improving translation quality. However, end-to-end speech translation is conceptually more suitable for fast inference than cascade system, but such evaluation hasn't been investigated so far. So I will focus on how to improve the decoding speed for end-to-end speech translation models. So before talking about the detail, I'd like to differentiate low latency inference from simultaneous decoding. Although simultaneous translation is a very important direction, but in this work, I will focus on decoding speed ups in the offline scenario. So for end-to-end approach has been investigated based on autoregressive decoder. In autoregressive decoder, the probability of target translations is decomposed into a chain of conditional probability from left to right manner. And the entire model is optimized with cross entropy objective. And during inference, the decoding is finalized when generating end of sentence mark. However, autoregressive left to right decoding still suffers from slow inference. This is because incremental decoding doesn't enjoy the fully enjoy the computational power of GPU and TPU and so on. So to speed up decoding, non-autoregressive decoder has been investigated in the text-based machine translation task. And the non-autoregressive decoder assumes conditional independence among output tokens. And to this end, it is necessary to predict target lengths in advance before starting translation. This is typically modeled by fertility model and the linear classifier and so on. So far, a lot of frameworks have been proposed in the text-based machine translation. And there are two categories. The first category is a single forward pass model. This category is very fast for decoding, but not so accurate. On the other hand, iterative refinement-based model are more accurate than single forward pass model by sacrificing some decoding speed. This category includes insertion-based model and mask-based model and energy-based model and so on. So the question is, what is the best modeling choice in end-to-end speech translation for non-autoregressive decoding? In speech translation, non-silence speech frames are not uniformly distributed over the input speech, and so the single forward pass model is not so suitable because it requires a copy of encoder output to initialize a decoder input. Although it is possible to use intermediate predictions from ASR submodule based on CTC, and this contradicts the motivation to alleviate error propagation from ASR by end-to-end modeling. So I will focus on iterative refinement model because it can flexibly trade the quality and latency during inference by changing the number of iterations. And also, we want to keep the trainability with auxiliary tasks such as ASR and MT because these subtasks are very effective to improve performance in speech translation. So to this end, I will focus on conditional masked language model, CMLM, in this work. And CMLM is easy to implement and achieve a good translation performance on variety of benchmark datasets. Okay. However, there are several challenges in non-autoregressive end-to-end speech translation. Firstly, the input sequence lengths can change flexibly because of pause duration, speaking rate, and language, etc. Moreover, even after the downsampling techniques, the input sequence lengths are much longer than output text lengths. It is possible to overcome this problem by rescoring multiple candidates from non-autoregressive decoder with separate autoregressive encoder-decoder model. However, input speech lengths are very long, so this extra computation for speech encoding is not negligible. To this end, I propose a new framework, Orthros, where the autoregressive and non-autoregressive decoders are shared on the same speech encoder. This is a unified architecture and can be trained in an end-to-end manner. During inference, we select the most probable candidate generated from non-autoregressive decoder by using scores from the autoregressive decoder. Since we can feed inputs to the autoregressive decoder in parallel, the additional computational cost is not so large. This is a system overview of Orthros, and there are 4 modules on top of the speech encoder. Non-autoregressive decoder, autoregressive decoder, CTC-based SR layer, and length predictor. And I will first describe the inference algorithm of CMLM. And the decoding algorithm is based on mask predict, where mask and predict operations are alternated for a constant number of iterations t. We first initialize the entire input with mask tokens, and in the mask operation, we mask out k tokens having the lowest confidence scores, and the number of mask token will be decreased based on the number of iteration steps. In the prediction step, we take the most probable token at every mask position I and update the hypothesis. And we take top L sequence length from length distribution provided from the length predictor, and we predict multiple L sequences having different lengths in parallel. And after the last iteration, we select the most probable sequence among L candidates. During training, we can use the cross entropy objective, but unlike the general cross entropy, we only calculate the loss for the masked token positions. The number of masked tokens is sampled from uniform distribution from 1 to the sequence length n. However, conditional masked language model suffers from mismatch between training and testing time. To bridge this gap, smart semi-autoregressive training was proposed. Here, we first obtain predictions at all positions by using current model parameter by feeding the masked reference tokens. Then we further apply new mask to predictions, and then this masked prediction will be fed into the decoder to calculate cross entropy. And then, and also, unlike the original CMLM, cross entropy loss is calculated at all positions, regardless of the number of mask tokens. Moreover, the gradient flow from the first iteration was truncated. This is a total training objective, or Orthros, and there are two objective functions: non-autoregressive decoders cross entropy, autoregressive decoders cross entropy, length prediction loss, and CTC-based ASR loss. During inference, we perform mask predict algorithm for T iterations. And then after the last iteration, we feed outputs from the non-autoregressive decoder to the autoregressive decoder in parallel. And then we pick up the most probable candidates among L candidates. Next is the experimental setting, and we will conduct experiments based on Massey English to German, English to French directions, and Fisher-Coulomb Spanish, and Libri-Trans. All the models were implemented based on ESP.NET ST, and we used transformer architecture. And to alleviate multi-modality problem, we used sequence level knowledge distillation technique for from text-based autoregressive machine translation teacher for non-autoregressive end-to-end models. And we measure translation quality based on foreground blue scores, and the decoding was performed with a single GPU, NVIDIA Titan RTX GPU, and we will report latency averaged over 5 runs. This is the main result on Massey, and latency was calculated in the English to German direction. Firstly, we saw that SMART significantly improved blue scores without extra latency during inference. Next, candidate selection with autoregressive decoder also significantly improved blue scores, and this corresponds to performing one more iteration, which takes additional 15 milliseconds latency. So we can think that CMLM doesn't have the ability to generate useful sentence level scores during inference. Next, we increase the vocabulary size from 8K to BP 16K. And large BP vocabulary was very effective for non-autoregressive model, but this was not true for autoregressive models, which will be shown in the later slide. Next, we further increase the model capacity of Orthros, and large capacity is very effective for Orthros. However, this was not true for autoregressive models, which will be also shown in the later slide. Okay, next I compared the model with autoregressive models, and the best Orthros model achieved comparable blue scores to the baseline autoregressive transformer. However, sequence level knowledge distillation also boosted transformer performance further, and this slightly differs from NMT literature because the text-based teacher is much stronger than end-to-end speech translation model because it can assume perfect transcription during training. This is a detailed latency and quality trade-off on massy English to German direction. First, we saw that larger length beam was not so effective when candidate rescoring was not used. In contrast, when we used candidate selection, we confirmed significant improvements of blue scores for every length beam width. In other words, larger length beam was effective in this case. And we can furthermore, we can achieve similar blue scores with a smaller iteration t. Next, we compared with autoregressive models, and Orthros achieved the same level of blue scores with 3 times speed up for greedy decoding and 1.5 times speed up for beam search decoding. Next, we increased the model capacity, and increasing parameters didn't improve the performance of autoregressive model so much. And with larger capacity, Orthros outperformed very strong autoregressive model in translation quality and latency at the same time. Next, we compared with a cascaded system. And as I mentioned earlier, cascaded systems were much slower than end-to-end models, and also end-to-end models achieved much better performance at the same time. Finally, we compared with candidate selection with external encoder-decoder model. And we confirmed that the unified architecture showed smaller latency and better blue scores simultaneously. And this is a result on Fisher-Kohlholm Spanish and Libritrans. And we confirmed the similar trend on these corpora as well. More interestingly, the non-autoregressive models achieved a very good performance, especially on Fisher-Kohlholm. This is probably because the input sequence lengths are relatively small, shorter than other corpora, and also the Spanish is close to English in terms of word order. Next is a aberration study on Fisher-Kohlholm dataset, and we saw that sequence level knowledge distillation was very beneficial for Orthros. And also, joint training with autoregressive decoder itself had no impact on blue scores. Here, we just train both decoders on the shared speech encoder, but we didn't use candidate selection during inference. Moreover, we also tried to investigate CTC-based length prediction. We first predict the source text length from CTC layer, and then performed length prediction with this expected source token length. However, linear classifier-based length prediction was better than CTC-based length prediction. Finally, I will show the effect of vocabulary size on Fisher-Kohlholm. Autoregressive models have a peak around BP1K. This is because of the data sparseness issue. However, Orthros with candidate selection continue to improve until BP16. And also, candidate selection with autoregressive decoder is always effective, regardless the size of BP. This is probably because the most token in the vocabulary are complete word, and also this has a complementary effect on the conditional independence assumption non-autoregressive decoder made. In conclusion, I showed two recent works on streaming SR and non-autoregressive decoding. In the streaming SR, I showed that alignment information is effective when applying it on the decoder side of Mocha. And CDC alignment is as good as alignment from hybrid system. For the fast decoding with Orthros, I showed candidate selection with autoregressive decoder was very effective to estimate target length from speech. And I achieved comparable translation quality to state-of-the-art autoregressive end-to-end speech translation models based on transformer with more than 2 times latency, twice latency reduction. Yes, that is. Thank you for attention.